Earth's orbit is crowded with millions of cataloged objects, debris fields, and unknown transients. On the ground, forensic labs process recovered metallic fragments of equally uncertain origin. The volume of uncatalogued material is vast. Current surveillance and materials analysis systems prioritize elemental composition. They are built to determine exactly what a material is made of, matching physical samples to known periodic tables. Knowing the exact ratio of iron to nickel in a fragment identifies the alloy, but it fails to answer the deeper question of how that specific alloy formed in the first place. We must interrogate the origin directly. We must ask whether a material's formation pathway is actually physically possible, given current established models of the universe. Isotopic Anomaly Fingerprinting, or IAF, is the specific scientific methodology designed to answer this forensic question. IAF evaluates the unique isotopic signatures left behind during a material's creation. IAF is a strict mathematical standard. It is not an interpretive tool, and it requires no theory of origin to function. Detecting an unknown object without proving its mathematical provenance leaves a critical forensic gap in materials science. IAF exists to close that gap. Every naturally forming material carries an isotopic fingerprint dictated by the specific conditions of its creation. Different extreme environments, from stellar nebulas to protoplanetary disks down to industrial furnaces, leave precise, recognizable signatures in the atomic structure of the materials they produce. This represents the stable solar baseline of magnesium isotopes. This flat, balanced distribution is the expected equilibrium for materials formed within known physical processes. Standard natural fractionation, the physical separation of isotopes, slightly alters this baseline, but strictly within predictable, documented limits. When a material deviates from this expected baseline, the deviation itself becomes the primary raw data. The scientific challenge is determining exactly how much deviation exists and establishing an objective threshold for when that deviation crosses from natural variance into anomaly. The natural baseline is the mandatory foundation of this work. Without a standard of equilibrium, anomaly cannot be quantified. Quantifying this variance requires a single, normalized mathematical metric. We call this the Isotopic Drift Index, represented mathematically as d-ISO. Looking at the d-ISO equation, we see exactly how this metric is derived. For each isotope, the formula calculates the deviation of the observed ratio against the standard baseline. Those deviations are normalized and summed into a cumulative score. This formula is theory-agnostic. It requires zero assumptions about a material's origin or history. It requires only a precise isotopic measurement and a published reference standard. D-ISO transforms complex, multi-isotope variants into one objective, undisputable number. This 3D bell curve maps the statistical distribution of the known natural sample corpus. The vast majority of standard materials sit calmly at the center, near zero. We define the boundary of this distribution at a specific threshold of d-ISO equals 0.50. We call this the Manhattan limit. Crossing this specific limit represents a 12 to 13 sigma deviation from the galactic norm. At this threshold, the isotopic data alone mathematically falsifies standard industrial melt phase processing as a viable formation pathway. The exact same threshold mathematically falsifies knives hill planetary formation pathways. The calculator only returns the limit mathematically. It identifies the scale of the anomaly, but it does not assign a cause to the deviation. The Manhattan limit acts as the definitive boundary between expected physical variance and true non-standard provenance. To prove the validity of this tool, we plot known reference samples along a horizontal scale. The first marker sits at 0.30 for NIST SRM 990, an industrial silicon standard. This score of 0.30 is anomalous, but definitively industrial and explainable. At 0.32, we plot an inclusion from the Allende meteorite, serving as an ancient solar system reference. Moving further right to 0.47, we introduce a pre-solar silicon carbide grain recovered from the Murchison meteorite. This 0.47 score is classified as inconclusive for terrestrial origin, yet it is scientifically expected given that the grain formed around a different star before our sun existed. Crucially, none of these extreme natural or industrial examples cross the 0.50 Manhattan limit. These calibration points prove the formula accurately identifies severe deviation without triggering false positives for known extreme materials. The D-ISO mathematical standard evaluates pure data. Because of this, it is entirely material and domain agnostic. In semiconductor procurement, applying D-ISO to isotopic gradients can authenticate microchips, protecting the supply chain against hardware spoofing. The exact same math applies to remote sensing. Spectroscopic data, measurements of light absorbed or emitted by matter, can be gathered from passing interstellar objects and run through the identical D-ISO formula. Returning to the horizontal scale, we establish the upper calibration point, 0.811, representing the Ubatuba fragment. Its provenance is highly contested, and Baird Research makes zero interpretive claims about origin. It is included purely because the published data anchors the metric's upper range. Whether evaluating a physical microchip, a recovered aerospace fragment, or a telescope readout, the standard applies uniformly across all sciences. Isotopic anomaly fingerprinting is purely a measurement methodology. It yields a number, not a theory. The BRSS calculator tool is a public utility where researchers can process their datasets and calculate D-ISO scores live. The tool features a full export workflow, generating time-stamped, reproducible PDF laboratory records formatted for direct inclusion in technical publications. We invite researchers across planetary science and materials engineering to apply this standard to their own datasets. The tool returns a mathematical truth. Interpreting what that truth means belongs entirely to the scientific community. True scientific rigor demands that extreme anomalies are no longer ignored, but mathematically standardized, rigorously quantified, and openly published.